All right, welcome to your Manova or Multivariate Anova lesson. This is finally we are doing multivariate analyses officially here in Psychology 524. Also, it is not a coincidence that it was a bunch of men who invented Manova and called it Manova. I don't know, like I feel like maybe if one of you guys wanted to come up with woman-ova and like what the W and the O might stand for, let's do it. Anyway, Manova is your multiple DV version of Anova. So we will spend some time going through what this means and what the possible use of it, where it might exist in psychology research. We're going to just use an example here from Schmidt 1994, a simplified version looking at humor and memory. So here's your tiny data set as a sample. We have humorous sentences and non-humorous sentences, and one dependent variable, which is number of sentences recalled. The theory might be that humorous sentences might be recalled more or better because of the humor. And so you could do an independent samples ANOVA here. We have not yet added in the second dependent variable. So we set it up like a regular ANOVA that you've done before. This is your deviation approach to sum of squares between. The sum of squares within value down there is a sort of a shortcut to get sum of squares within, but you may employ the deviation approach to that as well, or however you'd like to get those sums of squares values, which you probably have done before if you're studying Manova. This is your F statistic, comes out to 10.8. This is again for just an independent samples one-way ANOVA on the first DV. Your degrees of freedom formulas are there. The 10.8 is greater than the critical value. We reject the null hypothesis. Okay, that was the quickest ANOVA of all time. We went through fast because we need to get to our second DV, p-value 0.017. Okay, so there's a significant difference. Now we suppose that we have, memory could be assessed different ways, right? So we see this on exams all the time. We have multiple choice and we have free response and different ways of testing memory. So let's suppose we start with the suppose that we start with a free response task. That was the original DV. Now we add in a multiple choice task. And this is, there's a decision point here. Do you run two ANOVAs separately, or do you run one Manova? And the decision is, well, are our two DVs similar but different? And what I mean by that is they both represent memory in this case, right? Free response, multiple choice tasks, different forms of memory. So they are similar, but they're not exactly the same, right? Because somebody might do better on a multiple choice than on a free response or vice versa. So if the two DVs are unrelated, then you should not be doing an ANOVA. You should not be doing a Manova. If they are too much the same thing, then you should probably combine your two ANOVAs into one, or combine that DV into one and then just do an ANOVA. So the Manova is kind of like a compromise. You're not completely separating two ANOVAs from each other. You're not combining two completely similar DVs together. You're saying, okay, my two DVs are related to each other, but they're not exactly the same thing. So let's test them together first. And it's sort of like when you do an ANOVA followed by t-tests or something like that. You're testing them together first, and then you can always follow up with post hoc ANOVAs in this case. And so we'll take a look at what it looks like here. So we have our two DVs, free response, multiple choice, again, related but not exactly the same thing. The perfect setup for a Manova. And humorous and non-humorous sentences are assessed both ways. Hypotheses look exactly the same, except the group means are now based on a combination of the two DVs. And we'll see what that combination looks like. It all starts with Samuel Wilks and his Princeton lab in, I don't know what it was, 1940, maybe something like that, developing Wilks lambda. It's not W-I-L-K apostrophe S, it's Wilks apostrophe because his name was Wilks. So that's confusing where to put the apostrophe. But that's not the most important thing here. Most important thing here is the calculation. So we see S in bold print with a within. That's your sum of squares within, but it's sum of squares within for multiple DVs at once. And the bold print indicates that we now have a matrix as opposed to a single value to represent sum of squares within. Same thing with sum of squares between. We now have a matrix of values, and the matrix is derived from the multiple DVs, and we'll see how that plays out here. So it's as if you're going from a single correlation to a correlation matrix. Now we're going from a single sum of squares value to a sum of squares matrix for both within and between. Luckily, those matrices, when you only have two DVs, are not very large. They don't approach the size of a typical correlation matrix, certainly. We also see vertical lines here. The vertical lines are not absolute values. They are determinants of the matrices that we get. The determinant of a matrix we will see here in a minute as well. That is, it's similar to an eigenvalue in some sense because you're taking a matrix and you are trying to pull meaning out of it and convert it to just a single value. And so we'll see. Okay, so we start by doing the sums of squares calculations for the second DV. Okay, so we got to do that. This is, well, actually we don't have to do this, but it's good to illustrate what we're about to do with the matrices. And that is show you that 6.75, for example, is the group mean for the humorous group. 5.875 is the grand mean for humorous and non-humorous on the second DV. The second group mean there, non-humorous, is 5, and so on. And so we're going to need these numbers as we convert into awesome matrices. Okay, are you ready? If you need to pause the video and take a drink before we get into it, let's go. Okay, so all right, so this is what the beginning of it looks like. We're just taking our 4 people in our humorous group or 4 people in our non-humorous group. We're putting their responses to each of the DVs in matrix form. So that first person is 5 on the first DV and 8 on the second DV, and so on. Okay, we can do the same thing for the means here. So I'm going to start scrolling back and forth a little bit to match up the numbers with the position they are in the data, and so on. You can do this when you're trying to make sense of all the numbers, where they come from. I'm not one to put a bunch of symbols in there to represent different means. I'm just one to take an example and then pull the values from where they should be pulled from and then use the example as the illustration. So if you at some point need x's and x bars and different things to represent these different means, just let me know. We can put these in symbol form and then you can apply it to any example. But for this one, the 5 and the 6.75 there, those are the means for the humorous and non-humorous groups. So if we scroll back to, let's say here, the 5 there is the mean of the free response humorous group. 6.75 is the mean for multiple choice humorous. Then we have 2 and 5. Those are your means for the non-humorous groups. So the 2 is the free response mean for non-humorous, and the 5 is the mean for the multiple choice non-humorous. The grand means then are corresponding to the first DV and the second DV, free response and multiple choice, so 3.5 and 5.875. So we saw those. You can also see them in the calculations. For example, for the second DV here, the 5.875 is the featured value every time because that's the grand mean. All right, so moving forward into the sum of squares between calculations. Now this is just the same theory as what constitutes an Anova sum of squares for between. Goes with the Manova sum of squares for between. Sorry, just took a drink of my water. So that 5, was also long enough to pause you so that you could take this all in. All right, so we're going to have 8 terms, actually, 1 for each of the 8 people in the data set. So where is that 5 minus 3.5 coming from? Well, let's, again, scroll back to the data. Let's go back all the way to slide number 5 here. That's 5 minus 3.5, and that's going to exist for everybody in the humorous group on the first DV. So that gets plugged in matrix form, going back to slide 18 right there, and we're squaring it for an Anova, and the matrix version of squaring here is to take it in the first matrix and then multiply it by the second matrix. And so we're going to be doing some matrix multiplication and addition here. This is not a matrix multiplication and addition class. If you are going along and you realize that you need a review or a let's say, lesson on this arithmetic for matrices, you can refer to Tabachnik and Feidel's appendix. They have a nice little concise tutorial of how to do it. You can also just sit down with me in class or in office hours and we can go through it. But okay, so 5 minus 3.5, again, that is for the humorous group on the first DV, and you're squaring it by including it once in the left matrix there and once in the right matrix. And those will, the effect will be the same as squaring. Where did the 6.75 and the 5.875 come from? Well, now we're looking at the second DV, so we're going to look at 6.75 and 5.875. That's the humorous group on the second DV. And so what you're doing, you can kind of see it, hopefully, as it unfolds here. You're subtracting group means minus grand means. And so you're doing that for the first DV, and then you're doing that for the second DV. And whenever you're subtracting a grand mean from a group mean and squaring it, that is a sum of squares between groups because you are assessing how far apart those means are from each other, or more precisely, how far apart the group means are from the grand mean, and thus how different the groups are. Ultimately, what we're trying to tell, right, is the humorous group different than the non-humorous group on this combination of two DVs. All right, so the ... there, that suggests that you have 3 more terms, so that first multiplication gets repeated 3 times, just as it does like for the original Anova. So in the original Anova, we have 5 minus 3.5 squared, and that repeats 4 times. For the second DV, we have 6.75 minus 5.875 squared. That repeats 4 times. And so that's what that ... there is suggesting. And then same thing for the second term. So the second term is now the non-humorous group. So we've got 2 minus 3.5. That's for the, that's right here. That's the non-humorous group on the first DV. Free response, 2 minus 3.5 squared. You see it there in univariate form. Now we see it in multivariate form. And then the 5 minus 5.875 is again from the second DV and the non-humorous group. You see it there in the Anova 5 minus 5.875. All right, and again that gets repeated 4 times. Let's see the next slide. Let's move forward. So you can add all those matrices together, or since they're just repeated 4 times, then you can just go 4 times the whole thing. And then you're going to end up with 1 matrix at the end. Now, again, this is not a matrix multiplication class, but basically what happens to get that 18 there in the top left of that resulting matrix, you're taking 5 minus 3.5 on the left, multiplying by 5 minus 3.5 on the right. That's in your first term there. That's going to be 1.5 squared. And so you get that value. You then multiply that by 4, right? And that goes in the... So that value, that 1.5 squared, goes in the top left of your resulting matrix. Then you multiply that by 4, and you keep it there in the top left. Then you go to the next term. You've got 2 minus 3.5 multiplied by 2 minus 3.5. That's, again, 1.5. It's negative, but it's negative 1.5 squared, which results in the positive, same value. Multiply that by 4, and all of that added up comes out to 18. For the top right, I'll do that again because I'm just sort of talking over the formula here. That for the top right, you've got a 10.5. So for that one, you take 5 minus 3.5 on the left, multiplied by 6.75 minus 5.875 on the right. You're going to get a value out of that. Then you multiply that by 4. Then you pause, put it in the top right portion of the matrix. Then you go to the next term. You've got 2 minus 3.5 multiplied by, on the left, multiplied by 5 minus 5.875 on the right. And you'll get something there. Then you multiply that by 4. And then you add it to the first one, which was 5 minus 3.5 times 6.75 minus 5.875 times 4. And that gives you your 10.5. So you take the top left, multiply it by the left part of the matrix on the right side. And then you take the top left again, and multiply it by the right side of the matrix on the right side, and so on. And then you place your values accordingly. So it's not easy to necessarily dictate that to you without laying it all out for you. So if you want to go through this slide in person or in class, just let me know. And also, like I said, you can review the Tabachnik and Fidel appendix. Part of the appendix is devoted to matrix multiplication. So you end up with a 2 by 2 matrix, 2 rows and 2 columns, and that's what you need to get your sum of squares between multivariate. Now these 4 values don't necessarily hold meaning yet. We still need to take the determinant of them, and more precisely, we need to enter it into the Wilks lambda equation and get the sum of squares within as well. And it looks a little bit weird to have a sum of squares between on the bottom, but it just so adds up that once you get the sum of squares within here, you plug them in, the Wilks lambda is eventually going to convert to an f that is interpretable. And so we'll see that here in the process. Sum of squares within, meanwhile, is laid out similarly to the sum of squares between. But here, we just got to make sure that we are using the right deviations or the right, we're squaring the right things according to what a sum of squares within should be. And again, the theory is the same as it is for a univariate ANOVA in that we're taking our individual values and we are subtracting group means from them rather than for between groups sum of squares, right? We're taking group means and subtracting the grand mean from each of those. So again, I will try to dictate this a little bit and then we can go over it more in person as you wish. So starting with the first person here, 5 minus 5, so we go back to the first person. They scored 5 in the humorous category, and the subtraction of 5 is the group mean for the humorous group on the first DV. So it's 5 as an individual person's score minus the 5 there in the group mean for that person. That gets plugged in, so I'm going to go back to slide 21. That gets plugged in the top part of the left matrix there for the first person, and then also in the first column of the right matrix, 5 minus 5. The 8 minus 6.75 then is derived from the second DV, so let's look at that. 8 is the humorous group score for that first person. Again, this is independent samples, so that first person is only in the humorous group. But they do have 2 scores, one on the first DV, one on the second DV. So the second DV score there is 8 minus 6.75. That's the group mean for the humorous group on the second DV. And so then we plug that in the bottom left here of the left matrix and the right side of the right matrix. And when we multiply this out, it's as if we're squaring them. And so then that's the term for the first person. And the second person is going to have their own unique term. So the dot, 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 you got to be careful. You don't want to repeat that first term. You want to be careful. So like the second person in that group did not score 5, right? They still have a group mean of 5. But their first score was, let me find it, back to slide number 5. That person scored 7. So for that second person, it would be a 7 minus 5 instead of a 5 minus 5. And so each individual term here is going to be unique. So you just got to be careful on that. As long as you keep that first score, the individual score, and the second score, the group mean, you can do it once for the first DV, once for the second DV. And hopefully it makes sense by about the second or third time you do it. That last person, so this is the dot, 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 implies that we went all the way through the 8 people, and so that last one is the 8th person. So I can demo that one more time. The 1 minus 2, if you go back to the first DV, is in the non-humorous group. That person scored a 1, and the 2 was the group mean for non-humorous. So that gets plugged in there. And then the 5 minus 5 here is for the second DV on that same person. So that second DV non-humorous score was 5, and the group mean again was 5. So that's how you ended up with that. So one term for each of the 8 people. Again, these are unique terms for each of the 8 people as opposed to when we did sum of squares between. There was a little bit more repetition. Okay, so with some multiplication and addition, we're going to get the following 2 by 2 matrix here for this example. I recommend just trying it out, doing that multiplication, and see if you can get it for the example. If you can, then you know that you can get it on the homework. All right, so Wilks lambda then comes to be this way. We're going to do one more addition there in the bottom first. That is, when you're adding 2 matrices of the same size, you're doing 18 plus 10 in the top left, so you're going to get 28 top right is going to be 10.5 minus 3, and so on. So first you combine those matrices on the bottom, and then you take the determinant of each. Now the determinant, like I mentioned, is just a way of taking a matrix of values and converting it to a single score that means something. In this case, the determinant is going to give us a ratio that still isn't interpreted, but we're getting closer. We're almost there. So the operation for a determinant is just to take the top left, multiply by the bottom right, and then subtract top right multiplied by bottom left. So in this case, 10 times 8.75 multiplied by subtracting negative 3 times negative 3. That's your top half determinant, bottom half determinant you see there as well. And ultimately you get 0.218. And what do we do with 0.218? Well, time to take another sip of your drink if you'd like. We don't actually compare it to anything. We got to keep going for a minute. We got to convert it to an F distribution. So Wilks lambda falls on a distribution, but it doesn't fall on a distribution that allows for critical value and decision making just yet. So what it does do, however, is allow you to convert to F if you convert by this little mini formula here. So we're going to need Y, and we're going to need 2 degrees of freedom values. So the Y here is you take your Wilks lambda and you just put an exponent to it, and it's basically you're scaling it for how many dependent variables you have, and also how many groups you have in your within your independent variable. So in other words, in this case we have 2 dependent variables and we only had 2 independent variable categories, and so this was a pretty straightforward, like we didn't even have to put this in the exponent, right? Because the S there, the S is the number of dependent variables or degrees of freedom between, whichever is smaller. Well, in this case, degrees of freedom between was just 2 minus 1, so it was 1. So that goes in, and so basically you just keep your Wilks lambda here and switch it over to call it Y now. I think if you are doing an Anova and your IV has like 5 groups and then you have like 3 DVs or something like that, the bigger your design, in other words, the more this is going to change. But here we just keep it the same. So just note at this stage of your analysis how many DVs you have and how many independent variable groups you have, or your degrees of freedom between. Convert over. Here we don't need to do any converting in the end. It's just 0.218 still. We do need to get our degrees of freedom, and the degrees of freedom accounts for what we just did a little bit. It's related. So the degrees of freedom, the first value, number of DVs for us is 2. Degrees of freedom between those get multiplied together. You get 2. For degrees of freedom, the second value, you take that S. That S was 1 for us. That was like the previous slide. Number of groups minus 1 was the smaller value. So we ended up with 1 for S, and that goes out in front. Degrees of freedom within, which is your Anova degrees of freedom within, or the same thing as what you would have had for Anova. That's 6 in this case, so you just refer back to your degrees of freedom within formula for that from Anova. And then you've got this little fraction. Now, again, this is something where I don't know the exact theory about how this came about. This is a lot of simple math, but it's a lot of strange little mini conversions that I've never studied the reasons for. So if you are curious, you can look into it. Study, maybe go back to how Samuel Wilks came up with all of this stuff. Anyway, so if you're able to follow those relatively simple arithmetic operations here, you're going to get 5 for your second degrees of freedom. So your DF are now 2 and 5, and so then you put those into the back into the equation here with the Y in there. The Y was the Wilks lambda to the first power, which just came back as Wilks lambda, again, 0.218. And so your F now is 8.97, and now with a degrees of freedom of 2 and 5, we can interpret. Whew, we got there. All right, so based on that combo of DVs, we restate our hypotheses here. Test statistic came out to 8.97, greater than 5.79. All right, we rejected our null hypothesis, and I'm going to go ahead and show this to you in SPSS as well. because we're going to get a p-value 0.022. We can reject the null hypothesis and complete our Manova. All right, so let's look at this in SPSS. Here is your data entered. Basically, you just code it like an Anova here with humorous and non-humorous as your two groups, 1 and 2, and then just enter in your second DV. If you have, let's say you're doing an Anova, then you want to add in a second DV, you just add it in on the column to the right there. So we have free response. Here we could just do an Anova if we wanted, but then we're adding in the second DV, and we can go ahead and run that Manova. So I'm going to go to Analyze and General Linear Model and Multivariate. Maybe you had seen the Multivariate option here many times before, but you never actually tried to perform it, so now we're going to try to do it. Okay, so we're going to go to Multivariate. The setup for it is relatively straightforward, especially compared to what we just did by hand or written out. You're going to take your two DVs here, put them over to the dependent variable category. You take your group, you put it out in the fixed factor category. And there's other options here, such as post hoc Anovas, but I'm just going to click on OK. And we're going to see what the output gives us. So this is probably a little bit small on your YouTube viewer, but this is your multivariate Anova output. And what do we interpret? Well, they gives you some multivariate tests here, and it's going to give you those Wilks lambda values. You just got to look for it. So in this case, you've got intercept and group. Group is your independent variable in this case. So you're gonna there's other methods, there's other ways of getting a multivariate Anova test statistic. It's not, I guess, quite as agreed upon as an F statistic in Anova, in the sense that the mechanism by which you end up getting to the F statistic is a little bit different depending on whether you run a report of Pillai's trace or Wilks lambda or Hoteling's trace or whatever. So you'll see, and we will look at some of these empirical articles, you may see some of these other statistics reported, but if you notice, no matter which one you choose here in the group category, here's our Wilks lambda, 0.218. You get 8.97 as your converted F, and you're getting that no matter which mechanism you use to get to convert over to the F in the end. So again, there's a little bit more to this than I'm presenting to you as far as the choice of mechanism, how you get to that F statistic, but ultimately your p-value here resulting from the F is 0.022. Your degrees of freedom, it says hypothesis and error, that's DF1 and DF2, 2 and 5, and 0.022 your p-value. Okay, so flipping back to the notes for a minute, so we have the rejection of the null hypothesis here for Manova. P-value 0.022, less than 0.05, suggests that there is a significant difference between groups on some combination of free response and multiple choice. So the natural follow-up is to compare those free response and multiple choice questions as sort of, okay, where is the difference actually occurring, right? So, so this is restating your rejection of the null hypothesis. And now we can go see where the difference actually is, and we can do two Anovas. So I mentioned when we were on the SPSS output there that you could have selected something to get this. Actually, it just gives it to you automatically. So your box below multivariate tests contains those two Anovas, and you just have to hunt for it a little bit. It's under the group category again, and you've got free response here, sums of squares, degrees of freedom, mean square, and F, and then a p-value. And then the same thing for multiple choice, 6.12, that's your sum of squares for multiple choice, 4.2 your F, and so on. Okay, so we can go back and see where the difference really is. What that means is doing two Anovas. And for these, I actually went back to Tabachnik and Fidel, and I couldn't find what their recommendation was on like making a Bonferroni correction here. So I'm gonna go ahead and recommend it to be safe, just as if you're doing post hoc t-tests after an Anova. I would say, since you're doing two tests here, you want to be safe and correct for 0.05 and use 0.025 as your criteria here, 0.05 over 2 that is, when you're doing two Anovas, just to be a little bit more stingy here with your conclusion, considering you are doing two tests. But I've never been a big fan of those types of corrections. They do seem to me a bit arbitrary. So anyway, just to be safe. In this case, you're looking here back at the SPSS output. You've got group here, free response. That's your ANOVA for the first DV. 0.017 is your p-value, and so that is less than 0.025. So you would conclude a significant difference between humorous and non-humorous groups on the free response DV and not on the multiple choice DV, right? 0.086 greater than 0.025. So what you did here is a Manova. You determined that there was a difference on the DVs, some combination of them. Then you went in further and found that the free response DV actually contained the difference, or the significant difference, and the multiple choice DV did not. And again, this kind of goes back to like, well, maybe we should have just started with 2 ANOVAs in the beginning. And there's, again, this is a little bit up to you. But I think conventionally, and in my experience, submitting multiple ANOVAs to, let's say, this happened for my dissertation study. I submitted 2 different ANOVAs, and then the reviewer asked me to go back and do a Manova first to sort of clear the fact that, yes, there is some difference somewhere, and then I'm more authorized to do the 2 separate ANOVAs. So this is conventional. It's been happening this way, I believe, for many years for ANOVA researchers, multivariate ANOVA researchers. So that is recommended. All right, so going back to the notes, we're going to talk about two-way Manova a little bit, and I've got another example to run you through. This one, I'm not going to show you the Wilks lambda calculations and all that for the two-way Manova. I'm sorry. I know you were probably really looking forward to that. Okay, maybe not. Anyway, I'm going to run this through SPSS. This is a jumping jacks example that has been expanded based on, this is like, I gave you this example briefly in one of the review, I think it was the review notes from earlier in the semester. This is a jumping jacks example. So we start out with number of jumping jacks in 1 minute. We have experimenter gender and participant gender as our IVs, theoretically interacting in some way such that a female participant enters the room and is asked to do as many jumping jacks as she can in 1 minute, and she feels differently in front of the male experimenter as opposed to in front of the female experimenter. But then the male participant comes in, and it's a different scenario for him. Maybe he feels the reverse effect. He's more inspired to do jumping jacks in front of the female experiment. I don't know, something like that. You might imagine, though, that these 2 IVs might interact with each other. And we also might imagine that we have another way of measuring physical fitness, let's say, besides jumping jacks. So let's add in push-ups. And so we've got some data here. The way that it's organized for each DV in the notes here is for that first, let's say that top left group, we have 4 male participants on the push-ups here. They scored 30, 25, 12, and 13. And if you go back a couple of slides, those same 4 males did 8, 10, 10, and 12 jumping jacks. So those numbers correspond. The mean jumping jacks in that top left group was 10. The mean push-ups is 20, and so on. So we can enter this data into SPSS and talk about the results. If there is an interaction here, we might say the following. When the experimenter is male, males and females do the same amount of physical activity. However, when the experimenter is female, males do more physical activity. And we've changed the physical activity. It was originally jumping jacks, right? Without, if it was just one DV, the first DV was jumping jacks. Now we're expanding it to say physical activity, which is a general term to call for both jumping jacks and push-ups as 2 different related but not the same versions of physical activity and 2 different dependent variables as a result. So for the main effects, it's similar. We can follow up with ANOVAs, 1 for each DV, to see where the differences really are. All right, let's take a look at what this looks like. So here is your data for the two-way Manova. Again, it looks a little bit like a one-way, it looks like a two-way Anova at the beginning. You've got your 2 labeled categories there for your 2 IVs, jumping jacks is your original DV, and then you're just adding in another column next to it for the second DV, in this case, push-ups. Okay, so we're going to go back to Analyze and General Linear Model and Multivariate. We're going to put our 2 dependent variables over in the dependent variable slot, and we're going to put our 2 independent variables over in fixed factors. We can get some plots here if we want. I'm trying to keep it relatively simple, so I'm just going to click through and we're going to get the following. So this is just the same looking output as before with multivariate ANOVA in one box and the separate univariate ANOVAs in the other box below. So you just got to keep it all straight here. We're going to have two Wilks lambdas here. The first one for experimenter gender 4.488, the F value 5.77, P value 0.019. So it looks like there is indeed a main effect for experimenter gender, since that value is less than 0.05. For participant gender, it looks like the same result, 0.319 Wilks lambda, F, converted F, 11.746, p-value 0.002, so it does look like a main effect for participant gender on the combination of our DVs. And then for the interaction as well, 0.319 for the Wilks lambda, 11.746, same value for F, and 0.002 p-value. So those are your multivariate ANOVA, two-way MANOVA results. And so we start with that. Then we move down to the two-way ANOVA follow-ups. And so again, if you're converting, now we're running so many I don't know. I don't like these post hoc adjustments too much because they're, like I said, they're kind of arbitrary. But let's just use 0.025 again here because we have two DVs. So we're doing two tests per effect. So like the main effect of experimenter here, experimenter gender, we have two DVs. We're running one test for jumping jacks and another test for push-ups. So let's use 0.025 as our 0.05 over 2 Bonferroni correction. And if we use that, in this case, our p-values actually are both greater than 0.025. So even though we had an experimenter gender main effect, we have no individual. So even though we had an experimenter gender multivariate main effect, we don't have any experimenter gender univariate main effects. And this is a very small sample, so I'm going to blame that factor as our reason why we got an unusual result there. Usually you're going to get something in the univariate results to back up the multivariate result. So we'll blame small sample size. If that ever happens to you, though, let me know. We can talk about why it might have occurred in your real-life research. Participant gender main effects exist, it looks like, for both jumping jacks, 0.001 p-value, and for push-ups, 0.004. Same thing for the interaction. Looks like the interaction exists for jumping jacks, and it also exists for push-ups. So, of course, we would probably want to go back now and look up if the interaction is in the same direction, right? Because when you get an interaction, you might have, let's say, interaction cross graph, but then for jumping jacks, let's say, but then for push-ups, when you look at the graph, the lines are diverging or something like that. So anyway, you want to double check that at this stage, but for your purposes, this is just a mere introduction to two-way MANOVA, so you've got what you need here in your output to at least determine whether there is an interaction or not, both at the multivariate and then at the follow-up univariate level for each effect. All right, so back to the notes, just some tips to finish up. So I talked a little bit at the beginning about why MANOVA as opposed to just doing ANOVAs from the start. Well, first of all, if your DVs are too highly correlated with each other, you should probably combine them together and just do an ANOVA, or just get rid of one. Or if your DVs are uncorrelated near zero, then, well, you should just start with the two ANOVAs separately because your DVs are not worthy of being combined, right? You want to make sure that there is some cause for thinking that they are worthy of being combined together. Maybe there's a moderate correlation between them or some theory to suggest that they are similar in some way. So this is MANOVA's version of multicollinearity. There is not a given minimum for this correlation. So if there's a low correlation, let's say, between your DVs and there's theory to suggest that they could be combined, then you could probably just do it. However, the maximum is still 0.9 for sure. In real life, if you have a 0.7 or a 0.8 correlation, that's sort of cause for a red flag, and maybe you should be combining your DVs, but definitely if they're greater than 0.9. So this is MANOVA's version of multicollinearity. And then after doing all this, we find out that MANOVA should not be used. Well, you be the judge. So like I said, when I was a submitting my dissertation study to a journal, the reviewer asked for a Manova, so I needed to know how to do it, and so it is often requested when you are doing multiple Anovas in a row on dependent variables that are similar to each other. So it controls family-wise type 1 error, which is why we did that conversion, that Bonferroni correction from 0.05 to 0.025 when we did multiple Anovas. When we do the Manova, we do one test, we can keep our alpha at 0.05, and we can get a different sense of what's going on in our data. So I would not say that Manova is useless, but I am a fan. Actually, my bias is toward multiple analyses within reason, and not overly. I don't recommend grave concern over family-wise type 1 error when doing multiple tests. But certainly, if you're doing exploratory analyses and you're doing tons and tons of tests, you need to be a little bit careful. So always follow the scientific method. Well, unless you're doing factor analysis, but that's a topic for a different day, a different video. Okay, I will leave it there, and hopefully you guys learned something about Manova.